of the originally this was unitless or had units of angle, and now it has units of meters again, which is what we wanted. Okay, let's see. Can I? How do I just select and erase a big chunk? Or maybe just go on to the next page.
Just go to the next one, or use the eraser.
Okay, so last page. So we have dm over pi r. I equals dm plus y squared. Oh, sorry, there's dx dy up. And so we know from our change of coordinates, so we're going from x and y to r and theta. And so dx is going to be dr d theta. So that's one conversion. So we can now write dm is m over pi r squared r d theta. And so that's just substituting this relation in up here. And so then the last thing we have is what's x squared plus y squared in polar coordinates? It's, you said r? Okay, so we have, so it's close. So we have squared quantities here, right? So x squared plus y squared should be r squared, right? Okay. So bringing this all together, we have, let's see, m over pi r squared. And I guess maybe to make things more clear that this is a two-dimensional integral. Sometimes people will put two integrals like that just to signify that you're doing two different integrals. Okay, so this is our dm element. We have r dr d theta, and then we just have r squared. And so this is, you know, it's I guess what's the right way of saying it? You can kind of see already that, you know, one of the reasons, you know, circular coordinates are the natural choice here is, you know, this, I guess, not messy, but, you know, somewhat inelegant expression has just been replaced by r squared. So, you know, we're on the road to simplifying things here. And so then what I usually do is break these up. So I'll pull all of the constants out front. So we have m over pi r squared. And so then we have one integral over r, that the limits of integration are 0 to big R. And that, if we collect all these, we have r cubed dr. And then we have an integral over theta, which is, we're going over the full circle, so it's 0 to 2 pi. What is this doing? Okay, forgive the horrendous writing. Okay, so again, this is a lot of new stuff. Don't really worry if it's not exactly making sense or sinking in. Just, you know, keep in mind in general that these are some tools you have, and as you see it more and more, and you go over it several times, it's something that'll make a little more sense. But, so this integral from 0 to 2 pi over d theta, what's that integral equal to? 2 pi, right? So if I just kind of write the answer down below here, so we get 2 pi from that integral. So what's this integral from 0 to big R of r cubed dr?
R to the 4th over 4.
R to the 4th over 4. Okay, and then we have m over pi r squared out front. So we can cancel these pi's. This 2 cancels with that. We're left with 2. The r squared cancels with that. And so we just end up with 1/2 mr squared. So I know this got a little tricky. Oh, do you have a question?
I was just have a question about how you go from x and y to the polar coordinates, because dx dy is like the derivative of x and y, right?
Right.
And so then similarly, dr and d theta should be the derivative of r and theta.
Yeah, except so there's several ways you can think about doing this. One is basically that to get d theta. So d theta, again, since it's an angle, it's kind of non-physical. And so again, the quantity you really want is r times theta, which gives you the distance along the theta direction. And so the derivative of r times theta with respect to theta is just r d theta. And so that's why you end up with, r d theta rather than just d theta. This is something you can work out as well. It gets cumbersome and kind of painful. But you can write out, x equals r cosine theta and y equals r sine theta. And you can do derivatives, on all 4 variables and rearrange everything. And when you get to the end of that, you'll end up with the same answer here.
Well, if theta is equal to r d theta, right?
Or I guess maybe rather than saying theta is equal to r d theta, but the length element along the theta axis direction is r times theta. Does that make sense? Yeah, it's totally non-intuitive, and it's one of these things. Until you've worked a lot of problems and thought about it in different ways, several times, it doesn't usually sink in right away. So, don't worry if it's still a little confusing at this point. But, like you said, again, if you get into a bind and you don't want to deal with any of this polar coordinate nonsense, you can just do the integral by, either, like you said, converting it to a one-dimensional integral by writing one variable as a function of the other. You could also do it by doing one of the integrations that has limits that depend on the other variable. So it's not like these are impossible to do in Cartesian coordinates. It's just that they're more difficult.
What if it's pushed off center? Like, on this one it's pushed off center where the radius is 6 center?
Ah, right. So what you're talking instead of being so if your center of rotation moves to this location, so now if you're talking about using polar coordinates, defining the circle in polar coordinates from this point in the circle is almost impossible. I mean, that's going to be really, really painful to do. And so what you're going to end up wanting to do is go back to Cartesian coordinates in this case. And even in Cartesian coordinates, I mean, you can see already this is going to be a nightmare defining exactly, where all these points are. I guess now that I think about it, probably the easier way to do it is, well, gosh, yeah, I guess maybe leave your axis where it is and shift your variables. But yeah, so it becomes an unpleasant problem in that case. So, okay. Anyway, I think did you have anything to add, Nicole, or?
You or me?
Like 10 minutes.
Okay. So the origin here, and we have a stick sticking out here, and it's rotating like this. Do you guys remember what the moment of inertia for that was?